Electrochemistry. The things you know in electrochemistry. Conductance. Conductance is nothing but the reciprocal of resistance. That's the opposite of resistance. G is equal to 1 by R and the unit is per ohm. Specific resistance or resistivity. The formulas to be used here is rho is equal to R into A by L. L by A is equal to G, nothing but still constant. The unit is ohm centimeter. Specific conductance or conductivity both are same. Conductivity or specific conductance both are same. That is the conductivity of any conductor is reciprocal of specific resistance and it is denoted by kappa. Reciprocal of specific resistance. A specific resistance we can see the specific resistance or resistivity, that is rho is equal to R into A by L, and conductivity is a reciprocal of specific resistance and its unit is Siemens per centimeter. Unit is more important, don't forget that, and its unit is Siemens per meter. And molar conductivity, that is a conducting power of all ions produced by 1 gram of mole of an electrolyte in a solution. That is its molar conductivity. 1 gram of mole of an electrolyte conducts how much of electricity, that is called the molar conductivity of that electrolyte. That is denoted by kappa or lambda. Its unit is Siemens centimeter square per mole. Now, variation of molar conductivity with the concentration. Concentration in the sense there are two types of electrolytes. One is called strong electrolyte and weak electrolytes. And how the molar conductivity varies with the concentration of the electrolytes. For strong electrolytes, lambda, that is conductivity, decreases slightly with increase in concentration due to the increase in number of ions per unit volume. That is, it's an important question. For strong electrolytes, what happens when there is an increase in concentration? There is an increase in concentration. The space has been occupied and the ions are not free to move. Hence, there is a slight decrease in the conductivity. Right? Example, strong electrolyte case here. But in the case of weak electrolytes, it increases sharply with a decrease in concentration when it is diluted. When water is added to the weak electrolyte, when it is diluted, it increases the conductivity because the ionization has been increased because of the dilution. In the case of weak electrolyte, that is why the conductivity increases. Look at the diagram here. This is the concentration side. This is the conductivity side. In the case of strong electrolyte, what happens when the concentration increases here? This is the highest concentration. When the concentration increases, what happens to the conductivity? It falls down, right? Okay, the conductivity decreases as the concentration increases. As the concentration increases, conductivity decreases. But in the case of weak electrolyte, so you see here, what happens when the concentration decreases, the conductivity increases. Here the concentration part, here the conductivity. Look here, the conductivity increases when the concentration decreases, right? This is due to the presence of mobility of ions. But in the case of strong electrolytes, because it's concentrated, the ions are not able to move by adding further electrolyte in that. So that is a variation of molar conductivity with concentration. Right. Next, Kohlrausch law. Kohlrausch law states that the molar conductivity of an electrolyte at infinite dilution is nothing but is equal to the molar conductivity of its individual ions, the sum of the molar conductivity of its individual ions. Right? Let us have an example. The molar conductivity of CaCl2, that is equal to the molar conductivity of Ca2 plus and Cl minus. In your book, it has been given as NaCl. The molar conductivity of NaCl, that is equal to the conductivity of Na plus conductivity of Cl. Right. where we are applying the Kohlrausch law. For strong electrolyte, we can extrapolate the thing and we can find out the limiting molar conductivity. Right? If we extrapolate this, it will the curve will touch the conductivity and we can find out the maximum limiting molar conductivity in the case of strong electrolyte. But look at the weak electrolyte. Let me show it clearly. Yeah. Now look at the weak electrolyte here. If we extrapolate this one, it will goes on parallelly. It will not touch the conductivity line, right? It will goes like this. It goes on parallel, so that it is not possible to calculate the conductivity, limiting molar conductivity of weak electrolyte. Strong electrolyte we can extrapolate and we can find out. Weak electrolyte we cannot find out. For that, Kohlrausch law is used. Right? So what Kohlrausch law says that the limiting molar conductivity of a weak electrolyte that is equal to the conductivity of its component ions. Right? And also for calculation of degree of dissociation, alpha is equal to lambda by lambda naught, and also for calculation of dissociation constant Ka is equal to C alpha square by 1 minus alpha. These are the application of Kohlrausch law. There is three applications. One is for calculation of limiting molar conductivity, and another one is for calculation of degree of dissociation, and another one is calculation of dissociation constant. These formulas you have to put in mind for calculation part, right? These formulas you have to put in your mind always. Next, laws of electrolysis. Faraday first law of electrolysis, Faraday's second law of electrolysis. Faraday first law of electrolysis states that the amount of substance deposited during electrolysis is directly proportional to the quantity of electricity passed. W is equal to ZIT, right? The amount of electricity is directly proportional to the substance deposited during electrolysis. That is a Faraday first law. And Faraday's second law states that the amount of different substances liberated by same quantity of electricity passing through an electrolytic solution is proportional to their chemical equivalent weights. Is proportional to their chemical equivalent weight. That is, if a different amount of substances are liberated when we pass liberated at two electrodes, two different electrodes, when we pass the same amount of electricity, then that deposition is proportional to the chemical equivalent weights of that particular element. So that is the Faraday's second law. Nernst equation. This is the most important equation. This will definitely this problems related to Nernst equation will be in your paper. E cell is equal to E naught cell minus 0.059 by N. So here it may be written as 2.303 by NF. So the simplified form is 0.059 by N, log of concentration of the product by concentration of the reactor. And equilibrium constant Kc, E naught cell is equal to 0.059 by N, log of Kc. And at equilibrium, you have to understand that Q is equal to Kc and E cell is equal to 0. And Gibbs energy del Rg naught that is equal to minus N of E naught cell, del Rg naught that is equal to minus 2.303 log of Kc. So by using this formula, we can calculate either log Kc or E naught cell or del Rg, right? And here are some important products of electrolysis. If NaCl is taken, Na plus will be at the cathode and anode Cl minus will be at the anode. In the case of molten, but in the case of aqueous, this is most important. If electrolyte is molten or aqueous, that is most important. Remember, if it is in aqueous, what happens in the cathode? OH minus is liberated and anode Cl2 has been liberated. But in the case of aqueous, here sodium has been liberated. Here sodium will move towards the cathode, and at the anode chlorine is there. And in AgNO3, Ag electrodes, and cathode Ag will be there, anode Ag plus. And if in the case of platinum electrode, and cathode Ag will be there, and anode water, oxygen. Water logs will give oxygen. Electrochemical cell and electrolytic cell. So electrochemical cell, from the name itself, we can bring it that chemical energy into electrical energy. That is called electrochemical cell. That is which converts chemical energy into electrical energy. That is called electrochemical cell. An electrolytic cell, electrical energy into chemical energy, reverse process. That is called electrolytic cell. Right? The electrochemical cell is based upon the redox reaction, the spontaneous redox reaction. When spontaneous redox reaction happens, the chemical energy has been converted into the electrical energy. And in the case of non-spontaneous redox reaction, what happens that we have to give electricity for the reactions to take place. So that kind of reactions comes under electrolytic cell, right? And let us go for types of cell here. Mercury cell, the electrolyte is nothing but a paste of potassium hydroxide and zinc hydroxide, right? What happens the anode? In anode, the zinc gets converted into zinc oxide, right? And the cathode, the mercuric oxide gets reduced to mercury, and the overall reaction is zinc amalgam plus mercuric oxide gives zinc oxide plus iron. So this is a one-way reaction. So it provide constant energy. So this is the advantage or positive thing of mercury cell apart from the remaining thing, because it gives constant voltage and does not corrode due to the absence of ion in the overall reaction. The voltage, it will be standard 1.35, means standard 1.35 volt will be there always. And this is a primary cell. And dry cell, zinc chloride and ammonium chloride. So anode will be the zinc rod here, and the cathode will be the carbon rod. This is a normal clock battery what we are using. That is called dry cell. Pentar cell we'll call it na. So here the anode zinc rod and carbon surrounded by manganese. Anode zinc rod in the sense the outer coverage of the battery pack. That is the anode here, and inside there will be a black stick na, that is a carbon rod, and in between there is a paste of manganese oxide and ammonium chloride. But what happens here? At cathode, the manganese M1O2 gets converted into M12O3. And anode, the zinc gets converted into Zn2 plus. The electron released by the zinc, the electron released by the zinc is utilized by the cathode to produce ammonia and M12O3. So the overall reaction is zinc plus manganese dioxide plus ammonium ion gives Zn2 plus M12O3 plus ammonia. Here the role of here in this dry cell, there is a normal clock battery. This is corroded due to the presence of ion in the overall reaction, right? The zinc chloride is used to make a complex. That is the role of using ammonium chloride here. Ammonium chloride paste will be used here. That is used to make a complex with the zinc so that it serves a bursting of the cells. Bursting of the cells means it prevents the bursting of cell. And the standard voltage is 1.5 volt. The voltage, the output you can get from dry cell is 1.5 volt. Then coming to the next important interesting part, lead storage battery. That's a secondary battery. The important advantage of lead storage battery is it's rechargeable. The batteries what we are using in the cars, bikes, which or we are rechargeable batteries in even mosquito pad wherever, that are called lead storage battery. Here we are using 38% H2SO4. The anode is Pb grid and the cathode is Pb grid filled with PbO2, lead oxide. You would understand in both the cases. So in anode, the lead sulfate gets two electrons and it gives lead plus sulfate. And this sulfate ion reacts with the cathode, that is with the PbO2. This sulfate ion from the anode reaction reacts with the cathode and forms PbSO4, right? So the overall reaction is lead plus lead oxide. The lead sulfate dissociates into lead and sulfate here. That lead plus this lead oxide plus the sulfuric acid reacts together, use PbSO4 plus water. Right? If we recharge the thing, a reverse reaction will take place. The reaction takes place in such a way that the lead sulfate dissociates and give the product. Can be recharged by reversing the electrodes and the reactant become products and the product become reactants, right? So this is a lead storage battery. And another thing is fuel cell. Fuel cell, the important thing is we have to use KOH solution here. A fuel cell means we have to provide a hydrogen and oxygen put together. In anode, what happens? The hydrogen combines with the OH minus ions from the water. In center, water will be there. One side here in at anode we are passing the hydrogen and at cathode we are passing the oxygen. What happens here? The hydrogen gains a OH minus ion from the oxygen from the uh, water and forms H2O and releases 4 electrons, and that 4 electrons is utilized by the oxygen and water to form OH minus ions. The overall reactions, the hydrogen and oxygen combines together water. So this is eco-friendly and effective. So this is fuel cell. And corrosion. Corrosion is due to the formation of carbonic acid, H2CO3. So anode, what happens at the iron and Fe2 plus 2 electrons. Cathode, the oxygen plus the acid, whatever it may be, plus 4 electrons. And the formation of water takes place here. This Fe2 plus reacts with water and forms a rust Fe2O3. Right? So this is a reaction of corrosion. And prevention of corrosion, we know that by covering the surface by paint or spraying zinc, spraying some chemicals like bisphenol, or covering the surface by another metals like tin, zinc, etc. They are inert to save the object. An electrochemical method is sacrificial anode, sacrificial electrode like magnesium, zinc, etc. That will prevent corrosion. I already told you that in ships they are using the sacrificial anode. Zinc rods are used as sacrificial anodes. Then here, let us observe the graph. Let us observe the graph between molar conductivity and molar concentration. Here is a conductivity, here is a concentration. This is a curve we had already stated. This is in the case of weak electrolyte, this is the case of strong electrolyte. The curve is Y. The curve is Y for KCl or COH. Curve Y. The curve Y is for KCl or for COH. That is a question. So this is for weak electrolyte. So COH is a weak electrolyte. The intercept of CAPM axis for X is equal to dash. So that is a limiting molar conductivity. That is a CAPM of strong electrolyte here. The strong electrolyte is KCl here. Give you the mathematical equation representing the straight line. That is lambda m is equal to lambda m minus a root c. What is the slope is equal to? Slope is equal to negative of a. Right. What happens to the molar conductor on dilution in the case of weak electrolyte? This is what we discussed already. In the case of weak electrolyte and dilution, the conductivity increases because of the more number of ions and more spaces. Because of more number of ions as well as the mobility of ions increases. That's it, right? So this is for electrochemistry.